Hi everyone and welcome to Ask an Astronomer. My name's Jeremy Harwood and today I'm going to be giving you a talk on the Big Bang and the origins of the universe. Whenever I give this talk or one similar to it, I always actively encourage questions all the way through, and the reason is that there's some really tricky concepts we're going to be dealing with, and they're the sort of things that the greatest minds of the planet have been thinking about since the dawn of time. Where have we come from? Where are we going? And how did we get to be in the state we are today? So if you do have any questions, then either post them below or submit a question on the website or get involved with the forums, and we'll do the best to answer them as quickly as we can. But before we get to the Big Bang and where our universe came from, we need to think about what state our universe is in today. What does it consist of today? Well, there's the more obvious things that most people are aware of, so things like stars and planets. There's also a lot of dust and gas around in our universe. And there's also the more exotic objects. So we have things like black holes and dark matter, and also dark energy, which we'll come on to a bit later. And all of these objects are organised into large and small scale structures. So we have a star at the centre of the solar system with the planets going around it, and then we have all of these stars organised into galaxies which orbit around the supermassive black hole at the centre. And then these galaxies themselves are organised into clusters of galaxies where the large and small galaxies in a certain group are all interacting through gravity. But this hasn't always been the case. It hasn't always been organised into these nice structures which we see today. The way we view the universe has actually undergone quite a dramatic shift in recent times, and indeed it wasn't until just under 100 years ago we thought that the Milky Way was the entire universe. We didn't know of other galaxies or objects external to our galaxy, the Milky Way. And it wasn't until around 1922 that this guy Edwin Hubble came along, and what he showed was that there were objects that were so far away they couldn't possibly be part of our galaxy. They must be external to the Milky Way and be galaxies in their own right. And at this period of time, they thought the universe was actually in a steady state. And what we mean by that is that the universe is infinite in space and time. It went on forever, and it had been there forever, and it was always going to be there. But in 1927, a Belgian priest of all people came along and used Hubble's data to show that the universe was actually expanding. So it wasn't in this steady state that everybody had assumed it was and thought it was at the time. But the biggest limitations of these findings actually come from what he went on to say afterwards, in that if the universe is getting bigger, then in the past the universe must have been smaller. And if you carry that on, if you keep extrapolating that backwards and backwards and backwards in time, what you find is that the universe must have been, at some point of history, crammed into a single tiny little point. And he called this point the Primeval Atom. And this is what all of our Big Bang theories are based on today, the fact that the entire universe at some point in time was crammed down to the area smaller than a pinhead. And that's something really hard to get your head around. The fact that you, me, everything around you, the sun, everything you see in the universe, the earth, everything was crammed down to this tiny, tiny little point in an almost infinitely dense and infinitely hot state. And it was really thanks to people like Einstein and Niels Bohr with the birth of general relativity and quantum mechanics that we were really able to explain how this could be the case in any way, shape or form. And quantum mechanics actually sets a limit on how close to the start of the universe we can actually look, which is 10 to the negative 43 seconds, so 43 zeros followed by a 1. So a really small period of time, but there is a limit of how far we can look into before all of our known laws of physics begin to fall apart. And with the birth of our universe at the Big Bang, it wasn't just space that came into existence, so it wasn't just up, down, left and right which came into existence, it was actually time itself. So we're used to dealing with time either with a watch or a clock on the wall, but that's only really a measure of time. What we mean by time is the separation between two events occurring. And that's not something we really think about in our everyday life, and it's quite a tricky concept when you first come across it. We always have to bear in mind that the stuff that makes up you, me, and everything around us wasn't in existence yet. It was far too hot, and it was far too dense for anything really to exist as we know it today. But between 10 to the negative 36 and 10 to the negative 32 seconds, the universe underwent this rapid expansion, and it went from about the size of an atom to the size of a grapefruit, which doesn't seem like a lot, but it's about 10 to the 78 times its original size, so 1 with 78 zeros after it. And that's a massive, massive expansion to undergo in such a really short period of time. We're still dealing with split seconds. And when it was first suggested, it was quite controversial because we like to come up with theories and then go and see if they work, or try and explain something that is based on mathematics or observations. But this was really a sort of fill a gap to make a theory that sort of had some problems in it work. But in a way, we got lucky, because when we went back and looked with our more modern instruments and our modern techniques, it actually turns out that that probably was the case. So after this rapid expansion of the universe, we were still left with something that was in a very hot and very dense state. Remember, we're still talking about less than a second after the Big Bang occurred. And quantum mechanics and general relativity, and specifically probably the most famous equation in all of physics, E equals mc squared, means that matter can be created from energy. And that's what that equation means. Energy, E, is equal to matter times the speed of light squared. So under the conditions of the early universe, quantum mechanics allows that this matter was popping into existence pretty much out of nowhere, just out of pure energy. But it wasn't just the type of matter we're used to today that makes up sort of everything around us. It was basic elementary particles that make up things like atoms. But they're also always created in pairs. So you have this matter and you also have this antimatter pair. And antimatter is very, very similar to matter. In fact, it's identical in every way, except it has the opposite properties. So if a proton, for example, has a positive charge, an antiproton will have a negative charge. So as the universe continued to expand, it continued to get cooler. And after about 10 to the negative 6 seconds after the Big Bang, so we're still talking less than a second here, protons and neutrons and their antimatter equivalents as well were able to form. So that's the stuff that makes up the atoms that we know today. But obviously these collisions kept on occurring and annihilating each other. And these explosions are actually perfect explosions. So when you think of an explosion in everyday life, as much as you can have an explosion in everyday life, you know, there's smoke and, you know, there's all these flames and there's a lot of waste there. But these are perfect explosions. All of the matter is transferred into energy. But the probabilistic nature of quantum mechanics meant that there were 1 in 10 billion more particles of matter than antimatter. So in effect, matter won this battle for supremacy over what was going to dominate what we call baryonic matter of the universe, and all of the antimatter was annihilated. After a few minutes of the universe expanding and cooling, so we're at least out of the second realms now, it had cooled enough to undergo what we call Big Bang nuclear synthesis. And all this means is getting all these atoms, or the cores of these what will be atoms, and sticking them together. And we started to form things like hydrogen and helium and a little bit of things called deuterium, lithium, but not a lot else. It was around 75% hydrogen and about 25% helium, and there were tiny little bits, trace elements of other elements hanging around. But this matter and the radiation, so the energy and what we think of as light, is coupled together with the matter. And all we mean by that is that this light can't travel very far before it interacts with some of that matter and splits it apart again. So for the next 400,000 years or so, the universe kept expanding and getting bigger and bigger and bigger, and cooler and cooler and cooler, until the point that these photons, these packets of light, would have to travel before it had any good chance of interacting with any matter, was actually bigger than the universe itself. So this meant that the universe was very opaque, in where light couldn't travel very far between interacting with some matter, to being very, very transparent, where it could travel the entire length of the universe without really having a good chance of interacting with anything. So it became decoupled from the matter. And these form the earliest pictures we can take of the universe. You may have heard them mentioned a lot, especially in the last 10 years or so, called the cosmic microwave background radiation. And these really are the earliest images possible of our universe. And we can see from that image of the CMB that it's not perfectly smooth, it's not perfectly uniform. There's slightly denser regions. Those red spots are areas that are slightly hotter, and we have those dark blue regions which are slightly underdense, which are slightly cooler, and we're only talking about very small changes, very small variations in temperature. We're just looking at it with a really sensitive instrument. But over long periods of time, that little bit extra stuff where it's slightly hotter, slightly more dense, will draw in all the matter around it due to its little bit extra gravity. And those locations, those slightly hotter red spots, are where galaxies will eventually form, where the clusters of galaxies eventually form. But these periods were known as dark ages because no stars had formed yet. There was nothing to emit light. So it was a very sort of dark period. Then around 150 million years after the Big Bang, the first stars did pop into existence. They started to form in these early galaxies. And their light began to interact with the surrounding gas and heated it up again in a process known as ionization. And the light from these stars and the gas it encounters started re-emitting all this energy all over the place again. That light which wasn't there before was everywhere again, and the universe really lit up. And it took about 1 billion years for this reionization process to complete, for this light to interact and start knocking electrons off of all the surrounding gas and light the universe up to the way we know it is today. Then for about the next 13 billion years to the present day, galaxies have continued to evolve. They've merged in spectacular collisions, and even our Milky Way is one day destined to collide with its closest neighbour, the Andromeda Galaxy. And we tend to think in science, and especially in astronomy, that we're in no special place, but in our little local group at least, we're one of the heavyweights. Us and the Andromeda galaxies are quite big galaxies compared to the rest in our little local group, as it's known. And when they do collide one day, it's going to be a spectacular collision. But when we see these colliding galaxies, it looks like there's stars smashing into each other and all sorts of things going on. But in reality, the distances between stars and between all these objects in space is so great. It's only really the interaction with gravity we're seeing. It's the gravity of each star pulling on the others and the other exotic objects which are out there, and the gas sort of heating up and making these spectacular patterns that make some of the most awe-inspiring pictures that we see in astronomy. But we mentioned near the start that in the early universe there was only really hydrogen and helium and the few other trace elements about. So where did all the other stuff come from? Where did the stuff that makes us up? Where did the stuff that makes everything around us come from? And the answer to that is the stars themselves. So stars like our sun, over the course of their lifetime, changed the hydrogen in their core through nuclear reactions into helium. And when stars reach the end of their lifetime, they run out of hydrogen. They start burning that helium and turn it into other elements. And depending on the size of the star, this can carry on all the way up to iron. But after that point, it takes more energy to create that nuclear reaction than you get back out of it. So where do all the elements heavier than this come from? And again, the answer lies in stars, but in the way they die. Stars much bigger than our sun will end their lives in these massive supernova explosions, some of the most energetic events in the whole of the universe. And they fuse these elements together to create all of these other elements that we know. And a lot of these elements are what make us up and what make the stuff around us possible. So in a way, we're all stardust. So that's how we think how the universe got to the way it is today. But what about the future of our universe? Where do we think the universe is going? Now, originally we said that people thought the universe was in a steady state. It was neither expanding or contracting. And in fact, even Einstein originally thought so. He added extra terms into his equations to keep the universe in this steady state, and he called that his greatest mistake. But Hubble and Lemaitre showed that this really wasn't the case, and until the 90s it was thought that gravity would eventually win the battle for the universe. So there was this initial explosion at the Big Bang which pushed everything apart, pushed the whole universe apart. But eventually all the stuff inside the universe would attract together and pull the universe back to this single point. But we know that now to not be the case. The universe is actually accelerating. So it's not only getting bigger, it's getting bigger at an ever increasing rate. And this is rather counterintuitive, because if it's getting bigger faster, then what's causing it to accelerate? And this is what we call dark energy. But really, what is dark energy? And the short answer for that is nobody knows. Is it possible that our model of the universe is wrong, or the way we're measuring the universe is wrong? And I certainly know some people that believe that's the case. But as far as we can tell, it's a real effect, and the universe really is accelerating in its expansion. So assuming this is true, where does that leave the future of our universe? Well, there's two real cases to be made. One is that it will keep getting faster and faster and faster, and literally everything will be ripped apart. It will be accelerating so fast that it will be going faster than the speed of light, because there's nothing limiting the speed of the universe, just things going through the universe. But at the moment, the expansion of the universe only really applies to large scales. I mean, we don't feel the effects of the universe expanding. So there's a case to be made that gravity will always win on these smaller scales, and that eventually just everything will die out. The stars will eventually run out of fuel, and even the black holes will eventually flitter away through the loss of Hawking radiation. But the real answer is nobody knows, and people are working on it right now. They're trying to figure out what they think might happen, and it changes as we get new information and we get new evidence. And that's why it's always important to keep asking questions, keep trying to find out where the next step is. Then maybe one day we'll become close to finding the answer. I hope you enjoyed the talk. As always, please do ask questions or leave comments. We're always grateful for the feedback. If you want to ask a question, either leave it in the comments below or send it through the normal form on the website, or even tweet us or ask us on Facebook. That's why we're here after all, and we'll answer you as quick as we can. And we hope to see you all again soon.